Alright, so now we're going to move on to our next reaction type, single replacement. And in single replacement, you're going to know that it's single replacement because you have a free element and a compound, and it's going to form a new compound and a new free element. Not new meaning like new to the universe, but just like one that wasn't there on the reactant side. So, and it says if the free element can form a cation, it replaces a cation in the original compound. So let's just stop right there and show you what we mean by that. So as an example, sodium is a metal, therefore it can form a cation. It isn't a cation right now, it's just elemental sodium. It's probably solid sodium. And let's say it's going to react with some copper 1 chloride. Now, the compound is usually going to be aqueous, meaning dissolved, so the copper and chloride ions are floating around in aqueous solution. And so this is our single replacement reaction. So we have sodium, which can form cations, and the ionic compound copper 1 chloride. And it says that the free element, if the free element can form a cation, it's going to replace the cation in the original compound. Well, of course, we know that the copper is the cation because copper is positive and chloride is negative, so cation, anion. And so it's the sodium that's going to be replacing the copper. And so that's going to leave us with sodium chloride. And again, the compound, even on the product side, is usually going to be aqueous. And then the other product is going to be the copper that got sort of kicked out of the compound is now by itself. And it's elemental, it's not charged anymore, okay? So it's just going to be solid copper, okay? And it's not super critical that you understand the physical states right now, but just know that metals, of course, if they're in elemental form, will be solid. And then the ionic compound on the reactants and the product side is usually going to be aqueous for these. Okay, let's try another one. Let's say we have magnesium. So some solid magnesium, and it's going to react with some aluminum, let's say nitrate. All right, and that is our that's our ionic compound, and so it's going to be aqueous. All right, and so the magnesium, so there are two ions here. We have aluminum, which is our positive, it's three positive, and we have nitrate, which is negative. And so the magnesium, right now it doesn't have a charge, but it is a metal, and of course it's in group 2, which means it can get a 2+ charge if it's in a compound. And so that's what the magnesium is going to replace. It's going to replace the metal. Okay? So the magnesium will now be paired with the nitrate. Now, if we think about charges and balancing charges, magnesium, we know from the fact that it's in group 2, is +2. Nitrate is -1. So to balance these charges, what are we going to need? Right? We should say that we need 2 nitrates and 1 magnesium. Right? Okay, and then this is our ionic compound. It will be aqueous, and then the metal that got kicked out by itself now, and that's by itself, it's not in a compound, is going to be our aluminum. And so it's just going to be solid. Okay? Now the next statement says if the free element can form an anion, so a negative ion, it's going to replace the anion in the original compound. So an example of that might be if I have fluorine, and fluorine is a Brinkelhoff, it's diatomic, it's also a gas at room temperature. Let's say that the fluorine here is going to try to react with potassium chloride. Okay, that's aqueous. And then so what's going to happen here is the fluorine, right now it's not charged, but if it were charged, it would have a negative charge, right? -1 specifically. And so that's an anion. So the second little note here says if the free element can form an anion, and fluorine can, then that means it's going to try to replace the anion in our ionic compound. So in this case, we have 1 plus potassium and 1 minus chloride, and so our anion would be the chloride, right? So the fluorine is going to try to replace the chloride. And so that's going to give us now not potassium chloride, but potassium fluoride, right? And so potassium is 1 plus, fluoride is 1 minus, and so that's already balanced. And then this is our ionic compound, which is going to be aqueous. And then the thing that's by itself is now, the thing that got kicked out is going to be the chlorine. But chlorine, when it's by itself in elemental form, it's one of those Brinkelhoffs, right? Which means that it's not really by itself. It's going to have a 2. Oh, and I guess I forgot to balance the previous equation because I'm just now realizing that this one needs to be balanced. We didn't balance the previous one either. So if I go back up for just a second and balance our nitrates up above, it looks like we have 2 on the right and 3 on the left. So what I'm going to do is, just like balancing charges, I'm going to try to get to a least common multiple. So the least common multiple of 3 and 2 is 6. So I'm going to try to get to 6 on each side. So 3 in front of magnesium nitrate, 2 in front of aluminum nitrate. That also means I need 2 aluminums on the right and 3 magnesiums on the left. The last one, the most recent one we did, is easier because it just has 2 fluorines on the left. So that means we need to put a 2 in front of potassium fluoride on the right, and then a 2 in front of potassium chloride on the left. Okay, so the next step is, it says, note the free element on the reactant side must be more active than the element it is replacing. So what does that mean? Well, essentially, let's go back to our original problem. Sodium is going to try to replace copper, and we said that it did, and that's why we got sodium chloride and copper as our products. But we really should check to make sure that this reaction happens, because there are, with single replacement reactions, there is the possibility that we could have a no reaction. In other words, an unsuccessful attempt at a reaction. And so the thing that decides that is this activity series that you see on the right. So when a metal tries to replace another metal, we have to consult this little activity series, and you don't have to memorize this. You'll be provided this on tests and things. But what you want to ask yourself is the element that's by itself, so the sodium, is that higher on the list than the thing it's trying to replace, so the copper? And it turns out that sodium is right here, and copper is way down here, kind of towards the bottom a little bit, okay? And so yes, sodium is higher on the activity series, and the activity series just tells us what is able to replace what is more active. It's kind of like reactive, not exactly, not in the strictest terms, but you can kind of think of it that way. Your really unreactive metals are also low in activity, like platinum and gold. Okay, but copper is less active than sodium, and so sodium, being the one that's by itself, is going to be able to replace copper. So another example we'll do here. Let's go with, let's say we have, and by the way, the free element doesn't have to be listed first on the reactant side. So, for example, I might have like calcium bromide and let's say silver. Okay, and I'm just going to skip the physical states this time. So if you look at this, the thing that's by itself is the silver, right? And so it's a metal. It can form positive ions, specifically +1 ions. And so it's going to try to replace the positive ion in the ionic compound, and that's going to be the calcium. And so your next question, before you worry about predicting products, should be, will silver be able to replace calcium? It's always the thing that's by itself that's trying to replace the thing that's in the compound. And so silver is actually pretty low on our list. And if we look at this, silver is all the way down here. It's one of the very lowest, least active metals. And calcium is way up here near the top. So is silver active enough to replace calcium? All right, and there our answer is going to be no, it can't. And so instead of writing products and balancing, we are actually just going to say NR, and that NR stands for no reaction. Okay. We also do need to talk about ionic and net ionic equations. We're going to actually save those for a little bit later next week. And so when you get to assignment 4.2, it does ask you to, in addition to predicting products and balancing, to also step 3, it says, step 3, it says write the complete ionic equation and the net ionic equation is step 4. For right now, let's skip doing 3 and 4, and I'll explain that to you guys next week. So do go ahead and attempt those 4 additional problems. All right, thanks guys, and good luck.